In the last lectures, we have seen many different properties of the connectedness property of a topological space, and we gave different criteria or conditions when a connected space can be formed out of given connected spaces. And we also claimed in the last lectures that the real line is connected with the standard topology. Of course, we have already seen that the lower limit topology on the real line, with respect to that topology, the real line is not connected. But with the standard topology, it turns out that the real line is connected, and in this lecture we will try to prove this. Now the real line has the order property, the order relation. So for two real numbers x and y in R, x not equal to y, we have either x less than y or y is less than x. So the order property on the real line has many different kinds of now this order relation on the real line has various different kinds of useful properties, but we will focus on just three, and this will allow us to generalize this kind of relation to arbitrary sets. Now what are the properties that we want to focus on? So the first one is called non-reflexivity. What is non-reflexivity? It just says that we cannot have x less than x for any x in R. So this relation less than, strictly less than, we cannot have x is strictly less than itself for any real number x. So this is called non-reflexivity. The second property is comparability, which is just this thing I wrote above, that given x and y in R distinct points, then either x less than y or y is less than x. So this is called comparability. You can compare any two real numbers, distinct real numbers, with this relation, with the strictly less than relation. And the third one is called transitivity. What is transitivity? So given x, y and z distinct points, then x less than y and y less than z implies that x is less than z. So this is called transitive property of the order relation. So with these three properties, we can try to generalize these concepts to arbitrary sets in forms of binary relations. So let us define what is a binary relation. Binary relation. So a binary relation on, so let me denote it as R. R is just, so on some set, on a non-empty set, A is a non-empty subset of the Cartesian product A cross A. So remember that when we were defining a function, we had the rule of assignment, which was a particular kind of subset of A cross A, and here we are calling any non-empty subset of A cross A as a binary relation. So what is an example of a binary relation? Well, the rule of assignment of a function, as I said, is a binary relation. Rule of assignment associated with a function function f from a to a is a binary relation. Now we have already seen the strictly less than relation, and this relation is also a binary relation on this set of real numbers. Now we have already seen the order relation on R, which is the strictly less than relation, and this is a binary relation. So the relation strictly less than on R is a binary relation, and the subset of the Cartesian product given by the subset of pairs x and y such that x is less than y. This is a subset of the Cartesian product R cross R. So this is your relation as a subset, and this is the usual strictly less than relation on the real lines. So this is the concept of a binary relation, and now we come to the definition of a simply ordered set. Simply ordered set. So let A be a set, well, non-empty. A be a non-empty set. Then a simple order on A is a binary relation which satisfies the following properties. And these are the same properties that we wrote down for the strictly less than relation on the real lines. So first was non-reflexivity, which says that x is less than x for no x in R. Second is comparability, which is that if x and y are points in A, x not equal to y, then either you have x less than y or y less than x. So here I am denoting the simple order with the strictly less than sign. So this is note that A can be any general set, but to have an analogy with our strictly less than relation on the real lines, we denote our binary relation on A with the strictly less than sign. So our binary relation is a subset R of the Cartesian product, and we write x less than R if and only if x less than y if and only if the point x and xy belongs to R. So we use this notation for the binary relation, and we have these properties. So non-reflexivity, comparability, and then we have transitivity, which is that if x, y, and z are distinct points and x is less than y, y is less than z, then x is less than z. So this is a binary relation with some nice properties, and when this binary relation satisfies these kinds of properties, we call it a simple order. And of course we have already seen this for the case of the strictly less than relation on the real line, and this is this makes the real line as a simply ordered set. So let me just write it here. The real line with the strictly less than relation is a simply ordered set. Now, given a simply ordered set, we can give a topology on that set, which is called the ordered topology on that set. So what is the ordered topology? So the topology tau generated by the basis given by the following kinds of sets. So of course here let your A be the set and with the strictly less than sign be the simple order on A. So the first kind of sets are just the open intervals. So in analogy with the real lines, you have A, B, which is simply the set of points x in A such that A less than x and x is less than B. So just as we did for real lines, we can define this for any simply ordered set. And we have also intervals of the form A naught B open. So here we include A naught in the in this set. So this is the set of all points in A such that A naught, so first of all x equal to A naught or A naught less than x less than B, and here A naught is a smallest element of A. So if such A naught exists, so if your set A has a smallest element A naught, then we include the half closed interval from A naught to B. Similarly, we can define a interval A B naught where it is closed in the right side now, which is the set of all points in A for which x equal to B naught or A less than x less than B naught, and here B naught is the largest element of A if such a B naught exists. So assuming that A has either a smallest element or a largest element, we include these sets in the basis. So this topology tau generated by this the basis of all these the collection of all these sets is called the order topology on A. Now we have already seen an example of the order topology on R, and this is precisely the standard topology. So the tau standard on R is the order topology given by the strictly less than relation. Now on R2 we define a simple order as follows. Simple order as follows. So we write 2 points A, B and C, D. So both of them are in R2. So A, B less than C, D if either A equal to C and B less than D or A is less than C. So this is called the dictionary order on R2, dictionary order or lexicographic order on R2, and one can check that it is indeed a simple order. So I'll leave this as an exercise to check that this less than relation is a simple order. So you have to check the three properties, namely non-reflexivity, transitivity, and comparability. So with this dictionary order, this gives a new topology. Let me write it as tau less than on R2, the order topology induced by the dictionary order topology induced by this relation. And so what are the open sets in this topology? Well, if you have a, let's see, so if you have 2 points here, A, B, and another point on the same vertical line with A, so it has the same x coordinate A and a bigger y coordinate, let's call it D. So here A equal to C and B is less than D. So this means that the interval, so this line segment is open in this order topology on R2. Now you may recall that such a thing is usually not open in the standard topology on R2. So this interval, the interval AB to AD, so these are now 2 points and this is the interval. So this is a point, let's call it A0 and this is A1. So this is the interval A0 to A1 with the strictly less than relation. So this interval is not open in the standard topology. Why? Well, if you take any point on this interval and you take a rectangle or a Euclidean ball, then some points of it will lie outside this vertical line. So there is no basis set that is contained inside this vertical line in the standard topology. So in this sense, this means that tau less than is strictly finer than tau standard. Of course, if you have any open set in the standard topology and you take some point A, B, then there is a vertical line segment that contains it, and so it will be open in the ordered topology as well. So this set is open in tau standard as well as the ordered topology. So this means that tau, the ordered topology is strictly finer than the standard topology with the dictionary order. So now we can give some more concepts in relation to simply ordered sets, which are those of supremum and infimum of a set. So of a subset of a simply ordered set. So let A be a simply ordered set, and let us take any subset of A, B be any subset, non-empty subset of A. Then an upper bound, so let me define a few things here. So first of all, what is an upper bound for B? So an upper bound for B, this is a point x naught in A such that B is less than x naught for all B in B. So such a point x naught is called an upper bound for B. Similarly, a lower bound for B is a point, let me call it y naught in A such that y naught is less than B for all B in B. So this is the lower bound, and now the supremum and the infimum of this set B is the least upper bound and the greatest lower bound respectively. So the supremum of B, so usually denoted as sup B, is the least upper bound of B if it exists. So sometimes it can happen that a set has an upper bound, but it does not have a least upper bound. We will see an example of such a set. So it is the least upper bound of B if it exists. So this means that if it exists, it will satisfy the following property. So L, let me write L is the supremum of B if and only if for any upper bound x naught of B we have L is less than x naught. In fact, since L is the least upper bound, and so it's also an upper bound, we should allow L to be less than or equal to x naught. And here also in the upper bound and lower bound definitions, we should allow a point x naught to be an upper bound if B is less than or equal to x naught, and similarly for a lower bound y naught could be less than or equal to B. So it just says that an upper bound for B could be a point within B itself, and similarly a lower bound, and similarly for the supremum should be less than or equal to any other upper bound. So an example of a set which does not have a least upper bound is as follows. So take A to be the set 0 1 union 2 3, let's say, and B, so here the relation is just the strictly less than relation, usual less than relation on the real line, so with the usual less than relation. So this is a simply ordered set, as you can check. And now let B to be the set 0 1. So this is open at the point 1. Now any point in this interval 2 3 is an upper bound for A, but it does not have a least upper bound. But B does not have a least upper bound. Why? Precisely because we have left out the points 1 here and 2 here. So if you have the real line here and you have 0 1, so 1 is excluded, and then you have 2 3, 2 is excluded. So any point which is greater than 1, greater than so it is an upper bound for B, must lie in this interval 2, 3. So let us say it lies here, but because we have deleted the point 2, we can always find a lower value which is still an upper bound for B. So given any upper bound, there exists another upper bound which is smaller than that upper bound. So this means that B does not have a least upper bound. So similarly one can define the concepts of lower bound and infimum. So infimum is the greatest lower bound if it exists. And with these structures in mind, we can now define what is called a linear continuum, and this is again a generalization of the usual properties, order properties of the real line, and this in particular the real line itself is a linear continuum. So let me define what is a linear continuum. So here's the definition of a linear continuum. It says that a simply ordered set L with some relation which is again denoted as strictly less than, it is called a linear continuum if it satisfies these two conditions, first of which says that L has the least upper bound property. So what is the least upper bound property? It just says that any subset A which has at least one upper bound has a least upper bound or a supremum. So we have seen that the supremum may not exist, and the linear continuum, the first property of the linear continuum, it says that any subset which does have an upper bound must have a least upper bound. And the second property is the continuum part of this linear continuum structure. It says that if x is less than y in L, then there exists another point z such that x is less than z is less than y. So any set, any simply ordered set which satisfies these two conditions is called a linear continuum, and the main property of a linear continuum is that it is connected in the order topology. So theorem is that if L is a linear continuum, then it is connected in the order topology defined by the simple order. And so if we can show this, since R is a linear continuum, we will have the immediate corollary. So assuming that the theorem holds, we have that R is connected, because the order topology on R is just the standard topology. So in the standard topology, R is connected. So we will take up the proof of this theorem in the next lecture.